Welcome back to the deep dive. Just take a moment and think about it. The bridges you cross, the clean water you drink, the power grid keeping the lights on, all of that complex infrastructure, it speaks a kind of silent language, doesn't it? The language of engineering. But here in Canada, doing engineering, well, it's more than just having the technical chops. It's actually a legally defined privilege governed by acts in each province and territory. So our mission today is to cut through some of that legal jargon and really zero in on the core question for anyone stepping into this field. What is the official, legally binding definition of professional engineering in Canada?
That question, it's absolutely fundamental. It's the bedrock of the profession. And for those of you listening who are gearing up for the National Professional Practice Examination, the NPPE, look, this definition isn't just some abstract theory. It really sets out your identity as a professional, your scope of practice, and importantly, your liability. Getting the nuances wrong here means, well, fundamentally misunderstanding what your license represents. We really need to pull out the essential truth from the way these acts are written. The three key pieces: what engineers do, what public goods they protect, and the specific scientific knowledge they have to use.
Absolutely. And before we unlock that crucial definition, just a quick note. If you are on the path to getting your professional engineering license, or maybe you just want a deeper understanding of the legal and ethical foundations that underpin basically all Canadian infrastructure, now's the perfect time to subscribe to our channel. We craft these deep dives specifically to give you those critical insights, the shortcuts, the details you need to be successful on the NPPE exam. So go ahead, hit that subscribe button now. You don't want to miss these foundational discussions. Okay, so let's get into it. The legal identity of a professional engineer. One of the first things that jumps out from the legislation is, well, how remarkably consistent it is. Even though engineering regulation happens at the provincial level, the core definition of what constitutes professional practice is almost identical right across the country. That's pretty significant, right?
Oh, absolutely. That consistency is key. It tells you this definition isn't just a guideline, it's a hard legal boundary. It defines who's responsible, what requires a license, and where the enforcement power lies. The general definition, the one we can sort of synthesize from the different provincial acts, it might sound a bit dense, but honestly, every single word carries legal weight. It generally reads something like this. The practice of professional engineering means any act of planning, designing, composing, evaluating, advising, reporting, directing, or supervising, wherein the safeguarding of life, health, property, economic interests, the public welfare, or the environment is concerned. And that requires the application of engineering principles based on mathematics, chemistry, physics, and related applied sciences.
Wow, okay. That is comprehensive. But like you said, the key is breaking it down. I think splitting it into those three distinct parts you mentioned earlier is really helpful, especially maybe for remembering the scope, say, for exam purposes. So first up, we have the nature of the activity. These are the action words, the verbs we just heard: planning, advising, designing, evaluating.
Right, the doing words.
Exactly. They describe how an engineer actually engages with a problem or a project. Then second, there's the object of the activity. This defines the purpose behind the regulation. Things like life, health, property, the environment, public welfare, and interestingly, economic interests. This is the why.
A safeguarding aspect, yes.
And third, the foundation of the activity. This is the knowledge base. The legal text is super explicit here. Math, chemistry, physics, and related applied sciences.
Precisely. And those three components, taken together, they form the legal justification for why engineering is a self-regulating profession. It highlights the intellectual rigor needed and, crucially, the inherent accountability to the public. It's what makes professional engineering distinct from, say, routine technical work or a trade.
I want to pause on that second component for a second, the object of the activity. When you list life, health, property, and the environment, the need for safeguarding seems obvious. Public safety is paramount, naturally. But why is economic interests included right alongside them with seemingly the same legal weight? That feels like it could create some tension.
That's a really insightful question, and it gets to something core about engineering practice. Including economic interests explicitly acknowledges that engineers aren't just pure scientists in a lab. They're stewards of resources, of financial feasibility. Think about it. When a P.eng stamps a drawing, they're not just certifying that the bridge probably won't fall down that covers life and safety. They're also affirming that the design is fit for its intended purpose and economically sensible over its expected lifespan. That touches on property and economic interests. Liability can arise not just from a catastrophic failure, but also from, say, gross inefficiency or a structure that fails prematurely, costing the public or the client a fortune.
Okay, so it's about this constant balancing act, Safety, yes, but also sustainability, efficiency, value for money, all under this umbrella of professional legal responsibility. So if a design is perfectly safe structurally, but maybe it costs double what it reasonably should have because of poor planning or evaluation, that negligence hits those economic interests, and that still falls within the engineer's legally defined duty.
Exactly right. And that need for balance, it feeds directly back into that first component we talked about, the activities, those verbs. Let's maybe start with advising and reporting.
Okay, advisory roles, on the surface, they sound straightforward enough, giving advice. But the legal definition seems to imply a much heavier weight of responsibility than just, offering a suggestion. What does advising really mean in terms of legal liability?
Well, it's about high-stakes technical judgment, fundamentally. An engineer is called upon to provide an objective, evidence-based opinion. This could be to clients, maybe to government bodies or regulatory agencies. And independence is critical here. For instance, if your client hires you to design something and during that process while advising them, you realize they're pushing for shortcuts that could compromise public safety, your professional duty embedded in that definition requires you to flag that, to report it, even if it goes against their immediate economic desires.
What about when advisory roles bleed into policymaking? Like, say, an engineer advises a city council committee on updating floodplain maps or recommends priorities for major infrastructure spending. If, down the line, some unprecedented event happens, like a flood worse than anyone predicted, where does the engineer's liability actually sit? Is there a line?
There is a line. Generally, the liability is tied to the technical accuracy and the professional diligence of the advice at the time it was given, based on the standards and knowledge available then. An engineer can be held liable for professional negligence if they ignored relevant data, if they botched standard calculations, or if their advice wasn't truly independent. They aren't usually liable for absolutely every unpredictable future event, but they are responsible for failing to anticipate reasonably foreseeable risks based on current engineering practice and data. The legal framework holds them accountable for the quality and integrity of that intellectual service they provide.
That's a crucial distinction. Okay, let's move on to evaluating. This sounds a bit like the quality control or audit function within the profession.
In many ways, it is. Evaluation involves that systematic analysis needed to confirm if something, a design, an existing structure, a process is adequate, safe, or performing as intended. This is often where technical competence meets ethical integrity most directly. It involves tasks like reviewing another engineer's calculations, assessing failure risks in an existing piece of infrastructure, or signing off on the safety of a new installation. It's a cornerstone of quality assurance and regulatory compliance.
Right. I can just imagine the kind of pressure that might come up here, particularly on big projects with tight deadlines or budgets. The need to resist pressure to maybe approve work that isn't quite right. That must be intense.
It absolutely can be. The professional judgment needed during evaluation can sometimes be even more demanding than the initial design work itself. Because you're often dealing with real-world complications, maybe compromises made earlier, sometimes competing interests. Sound judgment here means rigorously applying your technical knowledge to spot any deficiencies and ensuring the work meets all the required codes, standards, and fundamentally ethical obligations. A failure in proper evaluation. That's often where the seeds of a future disaster are sown.
Which leads us nicely into designing. This is often seen as the creative engine of engineering, right, where innovation happens.
It is. Design is that whole process of conceiving an idea and then specifying how to build it, whether it's a sophisticated medical device, a sprawling renewable energy grid, or even a specialized piece of manufacturing equipment. It demands integrating all those scientific principles we talked about, but also factoring practical things like manufacturability, cognitive constraints, and critically managing risk.
And the ethical side of design feels huge here. Because essentially every choice made in a design, like the specific material you select, the safety factor you decide to apply, even the site location, each of those decisions directly impacts how resources get used and what level of long-term risk the public is exposed to.
Design is public safety in many ways. Ethical practice here demands that the engineer doesn't just design for normal operation. You have to anticipate potential failure modes, what happens under maximum stress, what happens if there's foreseeable misuse or error? It's about building in redundancy where needed and always upholding that non-negotiable principle. Public safety comes first.
Okay, let's pivot now to that third pillar we identified, the scientific foundations. The legal definition is really clear. The practice requires the application of engineering principles based on mathematics, chemistry, physics, and related applied sciences. This seems to be the key differentiator for a P.eng.
It really is the intellectual gatekeeper. The thinking is if you can perform the activity without relying on this specific scientific foundation, then it's likely not professional engineering under the legal definition. Let's start with mathematics. We're not just talking about arithmetic here. Math is the fundamental language engineering uses for quantification, for prediction, for modeling.
So we're into calculus, differential equations, maybe advanced statistics, numerical methods. How does that level of math connect directly back to those ethical duties, like safeguarding the public?
Mathematics allows us to quantify risk in a rigorous way. We use sophisticated statistical models, complex simulations, numerical analysis to predict things like failure probabilities, or to optimize how a system performs, or to determine just how large a safety factor is truly necessary. So, an ethical decision rooted in mathematics might be, for example, specifying a structural safety factor that bumps up the initial project cost by, say, 10%, but demonstrably, statistically, reduces the calculated probability of a catastrophic failure over the structure's 100-year lifespan. You see, that's a direct line from the scientific foundation, the math, to the ethical duty to protect both economic well-being and physical safety.
That really clarifies the connection. It's not just about solving equations for their own sake. It's about using them to build reliable, predictive models of the real world. And then physics comes in and provides the fundamental laws that those models have to obey.
Exactly. Physics gives us the non-negotiable rules of the game, the principles governing energy, forces, motion, heat transfer, fluid dynamics, material behavior. Whether you're designing an HVAC system for a building, analyzing the stresses on a bridge truss, or optimizing flow in a pipeline, physics dictates what's efficient, what's possible, and crucially, where the safety margins need to be.
So if a structure fails because of something like unexpected material fatigue under load, that could often be traced back to a failure in correctly applying physics principles or maybe material science to predict how it would behave over time.
Precisely. And that brings us to chemistry. It's sometimes the overlooked member of the trio, but it's absolutely vital, particularly for ensuring longevity, durability, and environmental responsibility.
Right. Chemistry gives us the understanding of things like corrosion, how materials degrade over time, the stability of chemical compounds under different conditions.
It dictates crucial material selection choices. An engineer needs a chemical understanding to know how concrete cures and gains strength, how different plastics might degrade when exposed to sunlight, or how certain metals will react in corrosive environments like salt water. And you apply chemistry when designing industrial processes to minimize harmful environmental impacts. Think about understanding combustion byproducts or chemical waste treatment. It ensures the long-term integrity of the materials you choose, which, again, protects the public's property, their economic interests, and the environment, often over decades.
And I guess modern engineering practice takes these classical sciences, math, physics, chemistry, and weaves them together with newer fields like advanced materials science, computational modeling, systems engineering, all aimed at creating solutions that are not just technically sound, but also sustainable and resilient in today's world. It's a constantly evolving knowledge base, but still legally grounded in those core sciences.
And if we pull all these threads together now, the specific activities engineers perform, the scientific foundation they must use, and the interests they are legally bound to protect you, see the bigger picture. This legal definition isn't just a technical specification. It's fundamentally an ethical commitment baked right in. It's a formal statement of a duty of care. It demands honesty, ongoing competence, and impartiality from every licensed engineer.
Yeah, and the consequences when that duty of care fails, they could be incredibly severe. We can't really talk about engineering accountability in Canada without touching on some historical examples. The sources often point to major disasters where negligence, a failure in fulfilling that defined duty, led to tragedy.
The Quebec Bridge collapse back in 1907 is a stark, classic example. That event fundamentally reshaped engineering regulation in Canada. It wasn't just a matter of steel failing, it was a catastrophic breakdown in evaluation and supervision key verbs in our definition. The records show that the engineers on site actually knew the design had issues. They'd observed significant buckling in key compression members as construction progressed.
But the work wasn't stopped, despite those clear warning signs. It sounds like a failure of judgment and professional oversight overrode the technical observations. 75 people lost their lives. How did a disaster like that directly impact the legal weight given to those terms like supervising and evaluating that are now embedded in the legal definition we've been discussing?
The Quebec Bridge disaster brutally demonstrated the absolute necessity for the engineer in charge, the P.eng, to have the authority and the obligation to prioritize public safety above all else, even above schedule pressures or budget constraints, even if it means halting a massive, expensive project. It really cemented the legal requirement for licensed professionals to be ultimately responsible for directing and supervising any engineering work that impacts public safety. It showed, tragically, that technical knowledge alone is insufficient without rigorous ethical application and oversight. That definition of scope we've been dissecting, it serves as that critical boundary marker today.
Right, that boundary marker is what ensures that these complex, high-stakes tasks affecting public welfare must be carried out, or at the very least approved, by a licensed professional engineer, a P.eng. It's the mechanism that prevents unqualified individuals from undertaking work that could endanger the public. It protects us all.
And that connects directly back to the whole concept of engineering being a self-regulating profession. The legal acts in each province grant the engineering associations the privilege and the responsibility to set the standards for who gets admitted, to monitor ongoing competence, and to enforce discipline when standards aren't met, much like professions like law or medicine. This detailed legal definition we've explored today is the absolute foundation upon which that entire system of self-regulation rests. It underpins engineering status as a learned profession with profound public duties.
That was a fantastic deep dive. A really thorough look at the legal and ethical DNA of a Canadian professional engineer. So let's quickly recap the main takeaways for everyone listening. We've established that the definition of professional engineering in Canada is a formal legal instrument, not just a description. It's built on specific, high-stakes activities like advising, evaluating, and designing. It's firmly grounded in a required knowledge base of specific sciences: mathematics, physics, and chemistry, along with related applied sciences. And crucially, it's intrinsically tied to a duty to safeguard public welfare, which explicitly includes protecting economic interests alongside life, health, property, and the environment. In essence, it defines your professional identity and accountability.
Absolutely. And reflecting on this comprehensive definition, especially the duty to protect those sometimes competing interests, it leaves us with a really important final thought for you, especially if you're heading towards licensure. Consider this. Given that explicit legal duty to safeguard economic interests right alongside the environment and public safety, how should you, as a professional engineer, navigate the complex challenge of balancing these three critical yet potentially conflicting concerns? Particularly when you're designing, say, a major new infrastructure project that needs to be economically viable and resilient for the next 100 years, all while meeting increasingly stringent climate standards and evolving environmental regulations. Wrestling with that critical balancing act, making those tough judgment calls ethically and competently, well, that's truly at the heart of professional engineering practice. Something for you to really mull over.
That is a perfect and very timely question to leave us with. A real-world ethical challenge. If you found this deep dive into the legal foundations valuable, and you want more expert breakdowns of the complex legal and ethical framework you need to master for licensure, then please subscribe now. Don't miss out on the essential information and insights we share to help you be successful on the NPPE exam. Thanks for joining us on the deep dive.